So in the last class we have seen compound pendulum and a bar pendulum, which is a case of compound pendulum. Again we will see today Keter's pendulum, which is also a compound pendulum. Now a Keter's pendulum is shown in this figure and it works on the principle of reversibility of center of suspension and center of oscillation. You've already seen this in the last class, and we've applied this in the case of bar pendulum. And this Keter's pendulum consists of a rigid rod made of a metal or an alloy of length of 120 centimeter and diameter 1 centimeter, fitted with two mutually facing and adjustable knife edges K1 and K2. The pendulum can be made to oscillate about any of its edges, any of its knife edges. So K1 and K2 in the figure are the knife edges. The knife edges are movable and can be fixed at any position of the rod. Here a capital A and capital W, that is these two weights, these two cylinders, are two movable cylinders kept beyond the knife edges, and capital B and small w, that is capital B, this one, and small w, this are two other movable small cylinders kept between knife edges as shown in figure. So the cylinders A and B are made of a metal or an alloy, and capital W and small w are made of wood or any other light material. So this is just to keep the pendulum asymmetric. This is to keep the pendulum asymmetric. That is, A and B are made of metals or alloys, while small w and capital W are made of wood or any other light material. So, but they are in the shape of a cylinder, so that the effect of the air resistance on the motion of the pendulum will be seen when the pendulum is reversed. We know if we reverse the pendulum, its time period will be same as we have seen in the case of compound pendulum. Compound pendulum, that is center of suspension and center of oscillation, can be interchanged. So even though the pendulum seems symmetrical, that is we have two symmetrically shaped cylinders on either side of the pendulum, but the weight is not balanced. That is, one side has alloy or metallic cylinders and the other side has a light weighted, maybe wood or any other light weighted material made cylinders. So its center of gravity will not be exactly at the center. Center of gravity will not be exactly at the center. It will be shifted towards the metallic or alloy cylinders where the weight is higher. Now initially we fix the knife edges with a distance of about 1 meter between them. The pendulum is first suspended from the knife edge K1, and it is then made to oscillate, and the time period of oscillation T1 is determined. So in this figure, so first we hang the pendulum in this knife edge and it is made to oscillate, and we determine the time period. So this time period, let it be T1, and now the pendulum is inverted and the time period of oscillation about the knife edge K2 is determined, and let the time period be T2 in case of knife edge K2. Now suitably adjusting the small cylinders B and W, the periods of pendulum about the 2 points is made exactly equal, so that T1 equals T2 equals T. That is, after determining T1 and T2, which are the time periods about K1 and K2 respectively, we try to adjust the small cylinders B and W so that the time period becomes exactly equal. Time periods T1 and T2 becomes exactly equal. So in this condition, when the time periods are equal on both the knife edges, the distance between the knife edges will be the length of the equivalent simple pendulum, which is capital L. So the distance between the knife edges will be the length of the equivalent simple pendulum. We can then determine the acceleration due to gravity using the relation we already seen, G equals 4 pi square L upon T square. Now, in practice, it is extremely difficult to adjust the cylinders to have exactly same time period. So we already said that we adjust the small cylinders to get the time periods equal. It is really difficult. Sometimes we are not, most times we are not able to get the exact time periods. So we have another method to find the acceleration due to gravity here. So if T1 and T2 are the time periods of oscillation about two centers of suspension at distances L1 and L2 from the center of gravity. Okay. So T1 and T2 are the time periods of oscillation about the two knife edges K1 and K2, and the distance of K1 from the center of gravity is L1 and distance of K2 from the center of gravity is L2. Now the T1 is given by 2 pi root over K square plus L1 square upon G times L1. So we've seen this expression in the case of a compound pendulum. Now the L becomes L1 here, since the distance from center of gravity to the knife edge K1 is L1. And similarly we can write for time period T2. There the value of L becomes L2. The remaining everything is same, and now we square and add. We square this term. This becomes T1 square equals 4 pi square times this term with the root gone, and same with T2 square. Now T1 square L1 is taken to this side, so T1 square L1 becomes this value 4 pi square upon J times K square plus L1 square. Again similarly T2 square into L2. Here T2 square into L2 can be written as 4 pi square times K square plus L2 square upon G. So subtracting the two equations, left hand side becomes T1 square L1 minus T2 square L2. Right hand side becomes 4 pi square upon G L1 square minus L2 square. On subtracting, the value K will be cancelled because K is common in both the equations. After subtracting, we will get this value. Now, I think you might know the method of partial fractions which you have learned in the schools. We can write the right hand side. We can write the right hand side as 4 pi square upon G can be written as this term upon this term. T1 square L1 minus T2 square L1 upon L1 square minus L2 square. So again, this term using partial fraction can be written in the form like this. Since L1 square minus L2 square can be written as L1 plus L2 into L minus L2 using the formula. And using partial fraction, we can write some constant by L1 plus L2 and some constant by L1 minus L2. So we determine the value of A and B. By simply taking the LCM here and equating the coefficients, and we get two equations, A plus B and A minus B, and using the elimination method we determine the value of A and determine the value of B. So you can just verify this step, this partial fraction and determination of the value of the constants. This is something you can do by yourself, which gives the value of A is obtained as T1 square plus T2 square upon 2, and value of B is obtained as T1 square minus T2 square upon 2. And substituting the value of A and B in this equation, we will get 4 pi square upon G in this form, and now from this we can get the value of acceleration due to gravity as this. So the important point here is that once we determine the value of T1 and T2 experimentally through by knife edges K1 and K2, we don't need to make T1 and T2 equal. We just can substitute T1 and T2 here and find the value of G, acceleration due to gravity. So the center of gravity is something we have to find, since L1 and L2 are the distances from the center of gravity. How do we determine the center of gravity? It can be known. It can be determined by balancing the pendulum on some knife edge. And the point of balance will be the point of center of gravity. Then L1 and L2 can be determined as well as T1 and T2, and hence G can be obtained. And in the simplest case, when T1 equals T2 equals T, it is when both the time periods are exactly equal and L1 plus L2 is some length capital L, then the expression reduces to the simple one, that is G equals 4 pi square upon L square, 4 pi square upon T square times L, 4 pi square times T square, 4 pi square upon T square times L.